Welcome back to OGLDEV. Let's talk about lighting. So it's pretty well known that everything that we see is the result of light rays that originate from some sort of a light source that hits an object and is being reflected into the human eye. The light source can be the sun, a bedroom lamp, street lights, or whatever. In terms of computer graphics, it means assigning some color to perhaps even a few million pixels, depending on the resolution. So we need to come up with some sort of a function where we would plug in various variables and conditions, and this function would return the color of each specific pixel. Since we cannot fully emulate the behavior of the actual light due to its complexity, we need to use a simplified model that can be executed in real time and provide hopefully good results. Over the course of the next few tutorials, we're going to study a very simple lighting model called the Phong Reflection Model. It's probably the first model that most people who are studying computer graphics are going to encounter, so you can find a lot of additional resources about it. This model was invented by a Vietnamese computer graphics researcher who unfortunately died at a very young age from leukemia. In the future, we will study newer and more advanced lighting models. Phong-based reflection is the result of combining three types of lighting components: a diffuse, specular, and ambient components. Each component contributes something to the overall image. The idea behind the diffuse component is that light illuminates a surface at its peak capacity when it hits it directly at an angle of 90 degrees between the surface and the light vector. So for example, like that. If the light is coming from the side, we're starting to lose some of its energy and it decreases the illumination. If the angle keeps growing until the light hits the surface from the back, then we get no reflection of that light from this surface. In the following demo, we have a diffuse light coming in from the left, and we can clearly see that we get the maximum lighting intensity on the side of the barrel that is facing directly towards the light. And as the barrel turns around, the triangles that are turning away from the light become darker until they disappear on the right-hand side. A good analogy would be the Earth spinning and creating the gradual transition between light and day. As you can see, there are a few points on the right that are lit, and we can also see the knob in the middle of the barrel. I guess this is because we don't have any shadows implemented yet. So the light simply flows through the barrel and it hits a few triangles that are facing it. We'll revisit this demo in the future with shadows. The specular component provides the appearance of shininess that some materials exhibit. We can see this in metals, marble, porcelain, and a few other materials. The location of the viewer also affects the part of the object that reflects back the specular component. So when we look at the object from one location, some parts of it will shine and others won't. And as we move around, the region on the object surface, which reflects the specular component, will also move. In this demo, we can see both diffuse and specular lighting. If we disable diffuse lighting, we can see that the area that reflects back specular lighting is very small. The last piece of the puzzle, the ambient component, I like to think about it as the solution to the problem that the diffuse component presents. Now, remember that between the diffuse and specular, the diffuse part is the major one because some objects are opaque, and when it's not opaque, the specular part is very small. The problem with diffuse lighting is inherent in its nature. We have maximum lighting when the light hits the surface straight on, and it slowly decreases as the angle becomes sharper, and then poof, it's gone. The light can no longer hit the surface, so we have absolute darkness. This simply doesn't look real, because in the real world we usually have some light bouncing back and forth all around us. So if you are on the street in the middle of the night with very dim street lights, even the shadows are not completely dark. You would still see something there. So if you find that the scene looks too dark, you can simply crank up the ambient component a bit until you get it right. Just remember to use it judiciously because too much ambient lighting might make the scene look bad. Okay, so we talked about the three components of light in the Phong model, but we must remember that there is another player in this game, and that is the object itself. In most cases, we expect the color of a pixel on the surface of an object to come from some texture. But in addition to that, the modeling artist can attach various material properties to the object that will affect the way the object responds to different light sources. In the hands of an expert, the material system is a powerful tool. The combination of the properties of light with the properties of the material provides us with the final color of a pixel. For example, we can see that Blender allows us to define a ton of different material properties, stuff like metallic, specular tint, roughness, and many more. Blender knows how to handle these properties and use them to render an object. So if you want to mimic Blender's behavior, you would basically need to emulate Blender in your shader. In our simplified model, we're going to work with a subset of these properties, and specifically, since we're working with Assimp, we will make our material system compatible with the material system in Assimp. The material system in Assimp is also quite diverse and provides many properties, so we're going to bring in some of these properties one by one as we go along. The main three are at the top, so for every light component there is a corresponding component in the material. This way you can make some materials highly responsive to certain lighting condition, while other materials will be less responsive. The plan for today is to set up a framework that will allow us to make progress more efficiently. Specifically, I'd like to factor out the shader management code into a set of classes. This will help us reduce the size of the application code even further. In addition, we're going to focus on the ambient component today, since it is the simplest one to implement. We will load the ambient component in the material when loading the model in Assimp, and combine it with the ambient component of the light, as well as the texture color, in order to calculate the final color of a pixel. For now, it's important to consider everything here as a suggestion. You can eliminate some parts of it if you feel they don't contribute much, and you can expand other parts or bring in new attributes. It's not written in stone. So first, let's review the lighting equation, which for now includes only the ambient component. On the part of the light, we have the light's color and its ambient intensity. Up until this point, we haven't mentioned the fact that light can come at any color. During the day, we have a natural white light, and depending on the hour and the weather, the light may gain a bit of red or gray. In the case of an artificial light, the color can be anything you want. The color of light is important because you need to remember that what we think about as the color of objects is simply the part of light that they reflect back. If a pure red light hits a pure blue surface, then no light is reflected. This is an extreme example, but it reminds us to give some thought as to the color of light. The ambient intensity is a light attribute that defines the amount of light that every pixel is going to receive, regardless of the general lighting conditions. If an object doesn't receive any other light except the ambient light, and let's say that we have a white light and we set the ambient intensity to 0.1, the result will be an object that can barely be seen. If we set the ambient intensity to 2, the result may appear to be too bright. You can think of the ambient intensity as some kind of a dimmer knob that allows you to increase or decrease the amount of light in a room or a scene. In our lighting equation, we modulate the color of light by multiplying it with the ambient intensity. The second part of the equation comes from the object itself. Here we have the color that is sampled from the texture. That's the base color of the object at the current pixel. We modulate it by multiplying it with the ambient component of the material. Most modelers enable us to define how much, in general, an object responds to ambient lighting, and this factor goes into the ambient component of the material. When we multiply all these factors together, we get the final color at the current pixel. Okay, so let's begin our code review by going over the changes that I've made in terms of shader management. So far, the shader creation code was part of the main application code, and I'd like to factor it out to separate classes. So we have a class called Technique, which is declared in OGLDEV/include/technique.h. This class serves as the base class for all the techniques that we're going to develop. A technique is simply a shader program that does lighting, shadows, fog, pretty much everything. This class has a list of shader objects as a private variable and the shader program as a protected variable, so it can be accessed from deriving classes. We also have a public pure virtual function called init that every deriving class must implement, and this is where we do the initialization of the technique. In order to initialize a new technique, for example, to implement ambient lighting, we need to derive this class and call the protected method addShader for every shader file that we have, along with the shader type in the first parameter. This will compile the shaders one by one. After adding all the shaders, we call the protected method finalize to link the shader objects into the shader program member variable. So for example, in the current tutorial directory, we have a LightingTechnique that derives from technique, and in the init function, we call addShader twice for the vertex shader and the fragment shader, and after that, we call finalize. Notice that the first thing that we do here is to call the init function of the base class, and this is where we create the shader program handle. Okay, so we no longer need to explicitly create shader programs, it's all done right here. The addShader and finalize functions contain the same code that we previously had in addShader and compile shaders as part of the main application code. Everything was simply moved here. The only addition is that after we create a shader object, we add it to the shader object list so that after we finish linking the program in finalize, we go over the list and call GLDeleteShader on every object. It's very similar to C++, where after you link a program, you can get rid of all the objects. Okay, let's go back to the init function in our LightingTechnique class, and after the call to finalize, we have a series of calls to get uniform location, which is a protected method of the technique class. This is a very simple wrapper to GLGetUniformLocation so that we can fetch the location of the uniforms without having to provide a shader program every time. All the uniforms location here are private members of the LightingTechnique, okay? So no more uniform locations in the global section. In order to actually configure the values in the uniforms, we have several set functions that wraps one of the many GLUniform functions. So for example, we have set WVP, which takes the WVP matrix and calls GLUniform matrix for FV with all the required parameters, so you just need to provide the matrix. The last function in the base class is enable, which simply calls GLUseProgram with our shader program handle. So you can have multiple techniques in your code and you enable one technique, render some objects, enable another technique, and render a few more objects, and so on. That's it in terms of shader management. Remember that the LightingTechnique header and CPP files are part of the current tutorial directory, so that in the following tutorials, we can create new versions with new features, but you can always go back to the previous tutorials and compare the new and old versions. Now let's see the changes in the main application code, okay? We have a pointer to the LightingTechnique class here, and when we initialize the tutorial class, we allocate a new LightingTechnique object. We call init to set the shaders and stuff. We enable the technique, and we set the texture unit using this wrapper that calls GLUniform1i to set the number of the texture unit into the shader sampler. The only thing that we need to do in the render function is to set the WVP matrix through the LightingTechnique object rather than directly as before. You can see that the main application code is now much shorter because we no longer have addShaders and compile shaders here. Okay, so the last piece of the puzzle is the ambient lighting equation in the shader code, and for that we need a light source and a material. So in our LightingTechnique.h, I created a class called baseLight that contains the color of the light as a vector of 3 floats, which is initialized in the constructor as white light. And we also have the ambient intensity, also a floating point. It is initialized to 0, so we must set it in the application code to some value if we want ambient lighting. The LightingTechnique has a setLight function that takes a reference to a base light and updates the shader. We'll take a look at the implementation after we see the shader. For the material, I created a new header in OGLDEV/include called OGLDEV_material.h. The reason that the material is in the include directory and the base light is here in the tutorial directory is that we need the material in the basic mesh class, which is in the common area. We will simply expand the same material file as we move forward. Right now, the material class is super simple. We just have an ambient color as a vector of 3 floats, and it is initialized to 0. But we need to load the material from the model file, so let's go back to the declaration of basic mesh. I've included OGLDEV material.h at the top, and we have a new member for the material vector in the private section because we may have multiple materials in this model. We must resize this vector using the number of materials that we have, same as with the textures. Now, as we go over the materials in the init materials function, we check whether the material has an ambient lighting attribute by calling the generic function get of the SMP AI material class using the AI matte key color ambient macro in the first parameter and a reference to an AI color 3D structure in the second parameter. If this call is successful, we copy the ambient color into the proper space in our material structure. Now we need to get the material from the basic mesh class, and here we run into a small design problem. In our render function, we do a series of draw calls based on the number of submeshes in the model, and between draw calls we can easily switch textures because it doesn't require access to the shader. The material is a shader variable, but we don't have access to the shader from the basic mesh class, and we don't want such a direct access. We want to keep the shaders and the meshes separate. So for now, I have some hack in the getMaterial function where I just loop over all the materials and return a reference to the first material whose ambient light is different than 0. Don't worry, I will fix this problem later on. Now let's go back to the application code. We have a baselight private member in the tutorial class, and we set the ambient intensity to 1 in the constructor. The color is by default white, and in the render loop, we set the light and the material into the LightingTechnique. The light is coming from the tutorial class, and the material is coming from the base mesh object. Now let's go to the fragment shader, and we have several changes here. First, we have definitions for the base light and material. These are exactly the same as what we have in C++, only in GLSL. You can see that the syntax for declaring structures in the GLSL is also the same as in C++. We have a couple of new uniforms here, GLight and GMaterial. In the main shader function, we sample a texel from the texture and we multiply it by the ambient color of the material, which must be expanded to a vec4. We then multiply it by the color of the light, and finally by the light ambient intensity. Now, I'd like to show you how to update uniforms of structure variables. Let's go back to the LightingTechnique init function. The way this works is that you need to have a separate uniform location for every element in the structure. And you need to get the uniform location using this notation. For example,glight.color,glight.ambient intensity, gmaterial ambient color. You can even have structures within structures, and you will need to use a.b.c, etc. We can now take a look at the implementation of setLight that calls glUniform3f using the location of the light color, glUniform1f to set the ambient intensity using its own location, and we have the same thing in setMaterial with the ambient color of the material. Okay, So the model of the barrel that I'm using in this tutorial is a public domain model that came from this website right here. I'll put the link below in case you want to download it. It was created by James Ray, so thank you, James. Since Blender models are binary files, I exported the model to OBJ format, and I'm using Assimp as usual to load it from the tutorial. Once you've exported the model to OBJ, you get two files, winebarrel.obj that contains vertices, texture coordinates, normals, and indices. At the top of the file, we have mtl-lib that points to the material file winebarrel.mtl. So let's open it and see what's there. Okay, so in general, the OBJ syntax is very simple, so you can easily make manual modifications and see the effect. NS is the specular exponent, and we will use it when we get to specular lighting. KA is the ambient color, so in this case, it's white. KD, KS, KE are diffuse, specular, and emissions that we don't need right now. Okay, so I'm not going to go over everything. I'll just point out mapKD, which is the diffuse texture that our basic mesh is going to use. It points to winebarreldiff.jpg in the textures directory, so let's open it. Okay, so many textures are like that, simply stacking all the visual properties of the barrel as efficiently as possible. Okay, cool. So now let's try to run this, and oh my gosh, what is that? It's definitely incorrect. So if you've seen the previous video about Assimp, I told you that when you start picking random models from around the web, you may need to tweak the way that you export and/or import the model into your application. It's not plug and play, you know, and often doesn't work out of the box. For example, you may need to switch between left and right coordinate systems based on what your application expects. In this case, I had to get rid of the Assimp import flag AI process flip UVs, which flips the UV coordinates along the y-axis. It was part of the Assimp load flags that we use when we call importer.read file. Now it works okay. Let's change the ambient intensity to 0.1, and we can barely see the barrel. Let's set the ambient intensity back to 1 and do another experiment. Let's reset the blue channel in the ambient color of the material to 0, and we get this yellowish barrel because yellow is actually defined as 255 on the red and the green channels and 0 on the blue channel. Okay, so ambient lighting is just the first step, and I invite you to join me on the next videos as we continue this journey of lighting in OpenGL. I hope you enjoyed this episode. If you did, please hit that like button and subscribe. You can also support this channel at patreon.com/OGLDEV. Thank you for watching, and I will see you in the next tutorial.